So, problem chapter 12, number 1. An air-cooled condenser is reject 70 kilowatts of heat from a condensing refrigerant to air. The condenser has an air side area of 210 square meters and a U value based on this area of 0.037 kilowatt per square meter Kelvin. So it is supplied with a 6.6 cubic meter per second of air, which has a density of 1.15 kilograms per cubic meter. If the condensing temperature is not limited to 55 degrees Celsius, what is the maximum allowed temperature of inlet air? So A is equals to 210 square meters, or U is 0.037 kilowatts per square meter Kelvin. So our Q is 70 kilowatts and 1.15 kilograms per cubic meter. That's our density. And the condensing temperature at 55 degrees Celsius. So W is equals to 6.6 cubic meter per second over 1.15 kilogram per cubic meter. So that is equals to 3.739 kilograms per second. So Cp is 1.0 kilojoules per kilogram Kelvin. So LMID is equals to Tc minus Ti minus Tc minus To over Ln times Tc minus Ti minus over Tc minus To. So Q is U times A times LMID. So that equals to Q the 70 over 0.037 times 210 equals to 9.009 Kelvin. So next is our TO minus TI, that's equivalent to 70 over 5.739 times 11, that's equivalent to 12.197 K. So next is LMID, that is TO minus T1 over Ln times 55 minus Ti over 55 minus To. That equals to 3.8724. And next is our 55 minus Ti equals to 3.8724 times 55 minus 12.197 minus Ti. So our Ti is equivalent to 38.6. So chapter 12, problem number 2. An air-cooled condenser has an expected U value of 30 W per m squared times K based on the air side area. The condenser is to transfer 60 kilowatts with an airflow rate of 15 kilograms per second, entering at 35 degrees Celsius. If the condensing temperature is to be 48 degrees Celsius, what is the required air side area? So our given is our W is 15 kilograms per second, our C is 1.0 kilojoules per kilogram Kelvin. So our TO is equivalent to Ti plus Q over W T. So that's equivalent to 35 plus 6T over 15 times 1. So our TO is equivalent to 39 degrees Celsius. So next is LMID equals to TO minus T1 over Ln times Tc minus Ti over Tc minus To. So that is 39 minus 35 over ln 48 minus 35 over 48 minus 39, so that equals to a 10.878 K. So lastly, our Q is 60. Our next is our U. So 30 over 100 times A times 10.878, so equals to 184 square meters. So chapter 12, problem number 3, our refrigerant 22 condenser has 4 water passes and a total of 60 copper tubes that are 14 millimeters in diameter and have 2 millimeter wall thickness. So the conductivity of copper is 390 W per mk. The outside of the tube is fine, so that the ratio of outside to inside area is 1.7. So the cooling water flows through the condenser tube is 3.8 liters per second. So calculate the water side coefficient. If the water at an average temperature of 30 degrees Celsius, at which temperature is K equals to 0.619 W over mk, so and density is 996 kilograms per cubic meter, and N is 0.000803 Pa times S. So B is using the mean condensing coefficient of 1420 W per square meter Kelvin. Calculate the overall heat transfer coefficient based on the condensing area. So RA is water side coefficient, so diameter is 14 mm, so the equivalent to 0.014 meters. So RK is 0.614 W per mk. So our density is 996 kilograms per cubic meter, and our C is 419 joules per I think this kilojoules per kilogram Kelvin. So our V is equals to 3.8 times 10 minus negative 3 cubic meters per second over 60 over 4 times pi over 4 times 0.014 squared. So our V is 1.6457 meters per second. So our H over K is equivalent to equals to 0.023 times V over N raised to 0.8 times C V over K raised to 0.4. So our H is, so H times 0.614 over 0.614 equals to 0.03 times 1.6457 times 0.014 times 996 over 0.000803 raised to 0.8 times 4196 times 0.000803 over 0.614 raised to 0.4. So our H equals to 7.313 W square meter Kelvin. So chapter 10, problem number 10, a condenser manufacturer guarantees the U value under operating condition to be 990 W per m squared Kelvin based on the water side area. In order to allow the fouling of the tubes, what is the U value required when the condenser leaves the factory? So 1 over V O of 2 equals to 1 over V of 1 equals to A over O and HF times A1. So VO1 is equals to 900 W per m squared Kelvin. So 1 H over HFF equals to 0.000176 meter square meter times K over W. So AO over A1 is 1. So our V 1 over V O of 2 equals to 1 over 900 is minus 2 0.00176 times 1. So our VO is 1199 W per m squared Kelvin. So next is chapter 13, problem number 1, using the method described in section 13 to 5 and entering condition given in table 13, chapter 13.1. For example, 13.1 at position 4, compute the length of tube needed to drop the temperature to 36 degrees. Use proper values for refrigerant 22 table when possible. So at table 13, 1, position 4, temperature is 37. So our P 4 is 1425.8 kilopascals and our X 4 is 0.023 and V4 is equals to 0.001230 cubic meter per kilogram. Our H4 is 249.84 kilojoules per kilogram and our V is 5895 meters per second. So at position 5, so T is equals to 36 degrees Celsius, so ln times P over 1000 is equals to 15.06 equals to 2481.4 over T, that is 36 degrees Celsius plus 273.15. So our P5 equals to 1390.3 kilopascal. So our VF equals to 0.777 plus 2062 plus times T plus 0.0001608 T squared. So our T is equals to 36 and over 1000, so that equivalent to 0.00872 cubic meters per kilogram. And our VG equals to negative 4.26 plus 940.50 times 36 plus 273.15 over 1390 300 over 1000. So our answer is 0.01665 cubic meters per kilogram. So, chapter 13, number 3, a refrigerant 22, refrigerating system operates with a condensing temperature of 35 degrees and evaporating temperature of negative 10 degrees Celsius. If the vapor leaves the evaporator, saturate and is compressed isentropically, what is the COP of the cycle? If the saturated liquid enters the expansion device, and our B is if the refrigerant entering the expansion device is 10% vapor, as in figure 13, problem 3. So at table A6 at negative 10 degrees, so H is 401.555 kilojoules per kilogram. Our S1 is 1.76713 kilojoules per Kelvin. So at 35 degrees Celsius at constant entropy from tables A7, so H2 is 45.212 kilojoules per kilogram. So at 35 degrees, H3 is equals to HF equals to 243.114 kilojoules per kilogram. So H4 equals to H3, so COP equals to H1 minus H4 over H2 minus H1, that is 401.5555 minus 243.4114 over 435.212 minus 401.555. So our answer for that is 4.71. So next is our B is H3 equals to HF plus X times HG minus HF. So Hg equals to 415.627 kilojoules per kilogram. Our Hf equals to 243.114 kilojoules per kilogram. So our X is 0.10. So H3 equals to 240.114 plus 0.10 times 415.627 minus 243.114. So our H3 equals to 260.365 kilojoules per kilogram. So that's equivalent to H4. So our COP is H1 minus H4 over H2 minus H1. So that is 401.55 minus 260.365 over 435.212 minus 401.555. So our answer is 4.20. So problem number 4, refrigerant 22 at pressure of 1500 kilopascal leaves the condenser and rises vertically 10 meters to the expansion valve. The pressure drop due to friction in the liquid line is 20 kilopascal. In order to have no vapor in the refrigerant entering the expansion valve, what is the maximum allowed temperature at that point? So our P1 our P2 is equal to P1 minus G H over V. 1 minus delta P. So H is 10 meters, G is our gravity, so delta P is 20 kilopascal and P1 is 1500 kilopascal. So from table A6B equals to 0.8808 liters per kilogram or 0.00088808 cubic meters per kilogram. So our P2 equals to 1500 times 1000 minus gravity 9.81 times 10 over 0.0008808 minus 20 times 1000. So that is 1368.62 kilopascal. So from table 8 to A6, so our T2 is equals to 35.4 degrees Celsius. So next is problem number 6 from also chapter 13. The catalog of an expansion valve manufacturer specified a refrigerating capacity of 45 kilowatts for an certain value when the pressure difference across the value of 500 kilopascals. The catalog rating applies when vapor-free liquid at 37.8 degrees Celsius enter the expansion value and the evaporating temperature is 4.4 degrees Celsius. What is the expected rating of the value when pressure difference across it is 1200 kilopascals? So our velocity equals to C square root of 2 times the pressure difference. So refrigerating capacity is square root of 2 times the pressure difference in meters per second. Then our new refrigerating capacity is 45 kilowatts. Square root of 1200 over 500. So our answer is 69.7 kilowatts.